Reconstructing dynamic scenes in space and time is a long-standing and challenging problem in computer vision. After this problem had been approached based on RGB frames for some time, the community has also explored using event cameras as an input modality. Event cameras are neuromorphic sensors in which pixels independently and continuously track their intensity changes. This results in excellent temporal resolution and dynamic range of the captured information. However, since event cameras are still not widespread, previous event-based non-rigid reconstruction methods use only one single camera. In this work, we explore the use of multiple event cameras for this task. This should reduce input ambiguity and therefore improve reconstruction quality. Since multiple cameras are of course harder to set up than a single one, we investigate whether the improvements in quality can justify the added complexity. We propose dynamic EventNeRF. It enables general non-rigid scene reconstruction using multi-view event and sparse RGB data. We assemble a novel multi-view event camera setup, collect both synthetic and real multi-view event datasets of challenging motions, and propose a method that allows to synthesize arbitrary novel views at arbitrary timestamps. First, we split the whole sequence into short overlapping segments. We represent each segment with a temporally conditioned MLP. To supervise one of them, we randomly sample event windows T0, T1. Then we predict 3 views at T0, T1 and at the time of the reference RGB frame. We apply 3 losses based on these predictions. An event loss between T0 and T1, an accumulation loss between T1 and the reference RGB, and an RGB loss between the predicted and ground truth reference RGB. To evaluate our method, we compose a new synthetic dataset with multi-view event streams of large and fast motions. It contains 5 scenes with 5 training views and 3 validation views. We assembled a setup with 6 color event cameras. It is room scale and portable, hardware synchronized and calibrated. We employ fast EDI to deblur the captured RGB frames using the events. Please note that due to the low resolution of the cameras, the results we are showing here have been spatially upsampled. With this setup, we record the first benchmark multi-view simultaneous event and RGB dataset. It consists of 18 minutes of fast, non-rigid motions in the dark, with and without object interaction. For evaluation, we selected 16 sequences of 5 to 10 seconds each. On synthetic data, our method outperforms all of the baselines. E2VIT-based methods first convert events from each view independently to RGB videos and then train an RGB-based model. Due to multi-view inconsistencies of this process, these baselines fail completely. Methods based on using blurry RGB use 20 FPS videos as training data. They perform better than the E2VIT baselines, but cannot handle the blur. These observations are consistent across scenes such as dress, spheres, Lego, and static Lego. In the latter, we can see that E2VIT methods don't recover the static parts of the caterpillar, as it produces no events. As our method uses both events and RGB, it recovers the full scene just fine. With the real data, baseline performance degrades even more, as only our method produces recognizable results. E2VIT-based methods suffer from multi-view inconsistencies, which result in numerous artifacts in the results. We can attribute the poor performance of blurry RGB methods to the following factors. First, blurry RGB videos were recorded at only 5 frames per second due to the dim lighting conditions. Second, we show the results in slow motion, demonstrating that the methods can't interpolate frames with only 5 FPS training data. Our method works well, as it uses both events and RGB to model continuous time dynamic scenes. Similar observations can be made for bucket and towel tricks. Note that our model can reconstruct the shadows due to self-supervised background matting, and that it can reconstruct dark objects despite dim lighting conditions. We ablate our method on synthetic data. We test different backbones including NGP, TensorRF-CP, and hexplane. NGP fails on the sparse-view setting. TensorRF and hexplane are grid-based, and thus cannot propagate details across time well, resulting in artifacts and blur. Disabling event, RGB, or accumulation losses results in worse quality. These observations carry over to real data. However, when disabling accumulation loss or clipping, the model diverges. Using a single segment model for the whole sequence leads to blurrier results due to its limited capacity. We also assess the importance of the number of input views. We find that increasing the number of views does improve the quality. This is a strong indication that multi-view event camera setups can be worth the investment. Here we show various results with our multi-segment model. Note that for the towel sequence, we can reconstruct the complex motion of a highly non-rigid and textureless towel. Now we show various short sequence results. Small objects, ball and bucket. Large deformations, jump and towel A. Thin structures, guitar and towel tricks. Large and fast natural motions, dancing and towel tricks. In summary, we introduced dynamic EventNeRF, the first method for 4D reconstruction of general scenes from multi-view events and sparse RGB frames, producing state-of-the-art results in dim light and fast motion. Our experiments show that the quality indeed significantly improves by using additional input views, which can justify the usage of and additional research on multi-view event setups for 4D reconstruction. To the best of our knowledge, we present the first dataset captured with a multi-view event camera rig. It includes recordings of complex motions in challenging lighting. The code and data will be released publicly, so that despite the limited availability of multi-view event data, further research can continue to explore this modality. Thank you for watching.